let's talk about that Doppler shift. Here's the actual YouTube address if you feel like jotting that down. Another interesting place where you can sometimes hear the Doppler shift is if you're out and about, shopping or whatnot, and you hear an ambulance or a fire truck go by, police car. A lot of times, if they have a fairly even tone to the siren, so in other words, if the siren's not going, like that, but if it's going, do you like my siren? Anyways, if it's a fairly even tone, sometimes you'll hear it go down a pitch as it goes by you, right? And it'll stir up all the dogs in the neighborhood as well, so it's because they don't like that for some reason. All right, I wanted, I just went over the Doppler shift sound for you. I want to talk about radar Doppler shift, okay? And here's a picture that I actually borrowed this from the diagram, the homework diagram. And up above are my two signals, and we're going to think of these as radar signals. So like in the radar gun, you've got a receiver and a sender, an emitter of radar, and then you've got a device to listen or to receive the radar return signal, and so that'll be transformed into a little voltage on a wire, and that's what's measured. So the top signal in red, the second signal below that in black are the incoming and outgoing. Okay, so the black one in the middle, the second signal down, is the outgoing signal. And I designed this picture so that it would have a wavelength, a nominal wavelength of 30 millimeters, and that the return signal would be a little bit longer wavelength, 34 millimeters. Now that is approximately the wavelength where police radar guns operate. Okay, I don't think they publish the exact wavelengths and frequencies, but I think it's somewhere around 30 millimeters. Okay, now for extra safety, I put in the dotted line for the equilibrium of both of those, and then down below there in blue, you can see the beats, and that is the sum of both signals. So inside the radar gun, that would be both wires feeding into a new wire and adding, so the sum of voltages is going to look like this lower signal in blue. I wish these colors were better. Anyway, now here's kind of a close-up. I want you to look carefully at this. If you want to make a sketch of this. This is just like a little close-up of the outgoing and the incoming. So the outgoing is black on the bottom, the return signals in red on top. And here on the left side is where the two electromagnetic waves are pretty close to being peak to peak. The fancy word we would use for that is in phase. When they're in phase like that, you're going to have constructive interference. Right? Now, a little bit further down the pipe, let me get my cursor over there. Down here towards the end of this little close-up, you've got trouble. Because now, over here, you've got a bump almost right below a dip over there. So there you would use the word out of phase. In the colloquial terms, the return bump is behind the outgoing bump. All right? So inside his device, he has a standard frequency oscillator generating his radar waves. and then he's listening to whatever comes back, and he compares them. Now he's not looking at wavelength like this, but we can look at the wavelength. And the two waves are eventually going to be added together by the computer inside a thing. But this bump is about half a wavelength behind. Or you could say it's half a wavelength ahead, either way. It's out of phase by just about half a wavelength because it's a bump almost right up to a dip. Right? And when that happens, you have destructive interference. So that would be a region of flat water. All right, now let's go back to our diagram here. Okay, here's the outgoing signal, which I set to be 30 millimeters. And up here, the top signal is the return signal, and I set that to be 34 millimeters, slightly longer. Okay, so here's another way you can add this as a side note to your diagram. There are more wiggles in this diagram for the outgoing signal, the black one, the second signal down. The top signal in this diagram, bigger wavelength, Jasmine, so not as many wiggles, not as many oscillations. All right? Now they're pretty close though. But by the time you get to the far side, the black signal in the second line down is probably got a couple more oscillations, all right, than the return signal. Now, when that happens, you get beats. Now, down here is the sum of the outgoing and the return, and you get beats. And for this one, I figured out the frequency and then the wavelength. The beat wavelength would be about 255 millimeters for this pair of waves. Question? I calculated the beat frequency. That's and the beat frequency is not on here, Kane. Okay, so beat frequency is F2 minus F1, and then I use the wave equation, and we don't have the wave equation yet, but I'm going to show you how to do it. And so once you get the beat frequency, you can figure out the beat wavelength, if you know the speed of propagation of the wave. All right. Now, if these were audio signals, okay, two speakers, and this is what you'd hear. Okay, so then that's what we have. You know, the two tuning forks that we showed in morning lecture and that you guys hopefully looked at in the YouTubes from homework overnight. This is what you hear. You hear that wah, 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 that beat, that audio beat. Electromagnetically, you don't really, well, they could probably turn it into a sound as well, but what they really do is measure the frequency of the beats. And I'm going to go through the basic wave equation here with you so that you can so that we can look at the beat frequency formula, which is how the police nab speeders like me. All right, and so here's the basic wave equation. The speed of propagation, V, is equal to lambda, the wavelength, times the frequency. Now, we've talked about wavelengths. You know, the 10 feet or the 12 feet between Caroline and Darien. Or for us, for this section, it was me and Caroline on, me and Caroline on Tuesday, about 10 feet. And the frequency, we did that with the pendulum. You know, we timed it and then, figured out the period, and then 1 over that was about 0.45 hertz. So that's all stuff that we can know. So here's the little nomenclature there. Propagation speed. So for instance, You know, the speed of sound in air would be, it's about 343 meters per second at sea level. So that's what you'd put in there. And Kane, what you would do, you figure out, if you know the speed of sound or the speed of propagation, you know, you put in 343. And if you know the frequency, you know, F2 minus F1, then you can figure out lambda. And that's how I did it. And I did it on a spreadsheet, but I mean, that's the formula in the spreadsheet. Now, the speed of light, light has its own wave equation, and it's the same basic structure. C equals lambda F. C is the symbol customarily used for the speed of light. And the speed of light is about 300 million meters per second. Whoa. That is motating. 3 times 10 to the 8. We discussed it, or I wrote about it in the very beginning of the e-text when we talked about the definition of the meter. The definition of the meter is now defined as a certain fraction or a certain distance traveled by light in 1 second, or in a fraction of a second. Einstein's famous equation, E equals mc squared, the energy of mass, the energy of matter itself, even if it's not in a magnetic field, gravitational field, or any kind of field, just having some kilograms of mass, it's called the rest energy. E equals mc squared. M is the mass in kilograms. C is the speed of light. And it's actually c squared. And so that's his most famous formula, and that's what this c is. It's the propagation speed for light. If you've ever seen a cowboy movie, you know, where they, you know, like they put their ear to the ground, or they see some railroad tracks and they put their ear to the railroad track. You know, the speed of propagation through the earth, or the speed of propagation of sound waves through a steel rail, those are going to be different from the speed of propagation through the air. Speed of propagation through the air also depends on your altitude. You know, what's the barometric pressure? The air pressure, the ambient air pressure, is basically the controlling factor. So in the ocean, sound waves, they depend on the water pressure. And so what happens in sonar, you know, if you're in a submarine for the Navy and you're trying to listen to some Russians or something, and the Russians are really easy to listen to because their subs are really noisy, and they don't have as good subs as we do. But anyway, so we listen to them. And what you have to figure out is, you know, with sonar waves or whales, you know, they listen to other whales, you know, at huge distances. And what you have to take into account is that the wave will propagate at different rates at different depths in the ocean. So if the Russian submarine is up by the surface and you're 500 meters down, the speed of the sonar waves is going to change. So if you're trying to you're trying to time the sonar waves and then figure out the distance to the Russians, you got to take into account the depth, you know, the depth of the water, the temperature of the water, all that stuff. So there's a lot of variations and stuff, but they all have the same basic structure. Here's another variation, or another environment. There's a lot of scientists that study the sun, solar physicists. And one of the things they study is sunspots, these big magnetic storms that kind of implant themselves in the surface of the sun. And there's huge magnetic fields there, and there's huge magnetic waves, electromagnetic waves that are generated. And the wave equation in that environment is very complex, but it still has the basic structure of C equals lambda F. There's a little bit more calculus in it, stuff for lambda, because lambda changes and stuff depending on the density of the solar atmosphere and everything like that. But it still has a structure that looks just like this. Now, I say that so that you can now understand this formula. This is the one that is actually programmed into the police department radar gun. You know, they have a little onboard computer chip, and it only does one thing, figures out the speed. Now, I'm going to work this out with you. It's a ratio of the return frequency to the outgoing frequency. Okay, this is the basic Doppler formula that allows you to figure out the speed v, okay, I've circled it, as a fraction of the speed of light. Now, something that's going at 30 meters per second is 1/10 millionth of the speed of light, but we still have good enough electronics that we can pick up a very slow speed in this formula. C in the denominator, underneath that factor of V, is the speed of light. So that's 3 times 10 to the 8 meters per second below. And for your car, you're going to be going tens of meters per second. So it's a pretty small fraction. But the electronics are good enough to pick up the small difference in the return frequency. Right, now let me show you how it goes. If the car is moving toward you, F return over F outgoing is going to be greater than 1. Right? And that will happen if V is positive. Right? So this big, huge, gigantic square root. Now, you're not going to have to calculate with this on exam 3. Don't worry about that. But I do want you to see how your computer handles it, or how the police officer's computer handles it. Okay? So if V is positive, then that's like saying, okay, I've got some big number or small number of meters per second in the numerator. Right now, the example that I've got here is 150 million meters per second. Now, that's half the speed of light. Nobody here has a car that goes that fast. Okay, that half the speed of light. You don't even have 1% of the speed of light. But anyways, if you did have something going at half the speed of light, and it was emitting, or if it was reflecting radar from the radar gun, it would pick up this much of a Doppler shift. Right? Here's how it would work. 150,000 in the numerator here, or excuse me, 150 million in the numerator, 300 million in the denominator, means that V over C is going to be 1/2. All right, so up top here you have 1 plus 1/2. In the bottom you have 1 minus 1/2. All right, and so basically, so go ahead and jot this down. For this Cinci example, you have a big, gigantic square root. And inside it, it's 3/2 divided by a second quotient, 1/2. And that just works out to the square root of 3. And that's 1.73. So if your car's coming toward you, you're going to have a higher frequency, and this fraction is going to be greater than 1. All right? So the police officer measures the return frequency by listening to beats, and then they plug it into this formula, and then they get the speed. So what we did in this example, we plugged in a speed and got the fraction, 1.73. The police officer would take the fraction and then solve backwards for V. Now, what you guys make a note, untangling this formula over here on the left to get V by itself is a little bit of algebra, all right? And untangling to get V by itself, you'd square both sides and then do cross multiply and do a little bit of algebra and stuff like that. We're not going to do that, but the guys that designed the radar gun have done that, and they've programmed in a formula based on this one, V equals, and then a bunch of square roots and the ratio F R over FO and all that stuff. So the computer, the radar gun measures the two Fs, gets the beat frequency, figures out the ratio, then plugs that into the formula, and gets the speed. And that's how they get speeders. So let's review that in outline form. If the car is moving toward the policeman, the return signal is slightly higher frequency, and that's the example that we just did. That's going really fast towards the policeman. All right? That's in electromagnetic radiation terms, in astrometrical terms, astronomy terms, we would call that a blue shift. If the source is moving towards you, any light is shifted toward the blue end of the spectrum. All right? And you measure it by picking up the beats. If the car is moving away from the policeman, the return frequency is slightly lower, but you still get beats. You get beats, you figure out the ratio of the frequencies, ding, you figure out the speed. Either way, the beats frequency in the Doppler formula will either bust or not bust the speeder or the motor vehicle operator. So that's how they do it. And there's other ways to get speeders. You know what they do? They used to, I don't know if they still do it, but they're out west. They'll have police officers in airplanes, and they'll fly over the interstate straightaway, and they'll time cars between 2 mile markers. You know, they'll be able to see the mile markers from the air, and the guy is in the car. He doesn't know that there's a plane up there usually, but the cops will see him, and if it takes too much time or if he takes too little time between the 2 mile markers, busted. But if he takes the normal amount of time, you know, so many seconds between each mile, you know, like 60 miles an hour, that's 60 seconds per mile. 1 minute per mile. So if it takes you a minute, if the speed limit's 60, and you take 60 seconds between each mile marker, you're good. But if you take 40 seconds between each mile marker, you're going to get nabbed. Unless you're in Montana, where it used to be that there was no speed limit during the daytime. Can you believe that? And when I lived in Montana, there was no speed limit. On the interstates and a lot of the back roads, secondary roads, no speed limit. At night, there's a speed limit. But during the day, so then the federal government said, okay, you got to have a speed limit, 70 miles an hour or whatever it was. So Montana said, okay, we'll post a speed limit, 70 miles an hour during the day. Speeding ticket, $5. So they have a speed limit out there now, but you only have to pay $5 if they nab you. All right? And then a speed limit at night. But anyways, this is how it works. So waves, interference, beats, electromagnetic waves, radar frequency, police. Also, you see it at Major League Baseball. Watch Major League Baseball game. College baseball on ESPN or something like that. They'll have a radar gun to speed the pitcher. How much heat does the pitcher bring on his pitch? 100 miles an hour. That's a good heater. So yeah, radar guns. That's how they do it. And notice how this guy is kind of interesting here. See this? He's got two little round things here. One's to send, one's to receive. That's what they do. All right. Let's talk about harmonics. We had a little bit of vocabulary work in homework overnight. So we're talking about in chapter 7 around page 130. The textbook and other places use the terminology harmonics. I tend not to use that. But the fundamental that we observed Tuesday with the coil spring is good. And the second one that we did at a slightly higher frequency, double the frequency, is the second harmonic. The third harmonic is 3 times the frequency. That's the pattern for the harmonics. The higher the harmonic, the higher the frequency short of the wavelength. Now, harmonic is something that you'll see if, for instance, if you're an acoustic engineer, and actually I think electrical engineers that are working with circuits and stuff use the terminology of harmonics. But for me, in quantum physics, we usually use terms like excited states. And then the other word for the fundamental mode in quantum physics is the ground state. So make a note of that. Just a little vocabulary. And I tend to think in terms of ground state and excited states. The ground state is the lowest possible state for an electron, the lowest possible energy state. Electrons are described by their energy and their angular momentum states. Electrons in atoms. And so the ground state is the lowest possible energy state. But yeah, I mean, if you're, and here's another thing that I want to point out to you. This is about acoustics and music and stuff. If you've ever noticed, you can have two people, in fact, two instruments, like a guitar and a piano, and if they're trying to tune to each other so that, if the piano's in tune and the guy with the guitar has to get tuned up, he'll use the piano to tune his guitar, or he can. But they sound different. A G on a guitar is different from a G on a piano, and a G on a piano is also different from a G on a trumpet. Now, if they all three of them play at the same time, it'll sound melodious, it'll sound nice, but they don't sound the same. And that's because the sound waves from a guitar, violin, piano, trumpet, flute, any other normal instrument is going to be a mixture of the harmonics. So make a note. Different musical instruments have different mixtures of the harmonic. Now, of the higher harmonics. So the fundamental mode, the first harmonic, is usually the loudest. But if you pluck a guitar string, you're going to get a little bit of sound energy in the second harmonic, and a little bit of sound energy in the third harmonic, and so on up the scale. And it'll be a different mix. If you pluck the same string, the G, for a piano, it's a different kind of a wire. It's bigger, okay, and it's tighter. And that's going to generate, loudest in the in the first harmonic, but then different proportions. It might have 1% in the second harmonic, and 0.5% in the third harmonic, and then 3% in the fourth harmonic. It just depends. And that mixture of harmonics is what gives each musical instrument its distinctive sound. Same thing if Darian were to sing a middle C. If Darian was to sing a middle C and compare that to a piano middle C, you'd know the difference between Darian and the piano, of course. Everybody would know that. And that's because the human voice is a complex mixture of harmonics. And that's if you sing one note. And if you're speaking like I am right now, that's a huge mixture. But, it can be analyzed. Now, the exception to all this is electronic devices. So if you have a synthesizer, if like you have an electronic keyboard at home, up on its stand, and you press one button and you can make it sound like a trumpet, and you press a different button, it'll sound like a flute, and you press a different button, it'll sound like a regular piano, and if you press another button, it'll sound like, they even have, like my son, he has a Yamaha. That's what it is. It's a Yamaha keyboard. And you can get different sounds, different mixtures of the harmonics. Okay? But you can also get a pure tone in an electric device. That's the only way to get a really pure one. Musical instruments, regular instruments, violins, guitars, pianos, they sound lovely, but they're not going to generate a really pure tone. Not the way, but you know, pure tones, they suck. You know, they're not that, I mean, they're nice if you're a robot or something like that. But a human being is going to say, what am I, in a science fiction movie or something? You know, because we like complex, we like complexity. And, you know, we're designed to listen to complexity. And that's in the mixtures of the harmonics. But, you know, if you have a good synthesizer, you generate a bunch of pure tones, and it sounds cool, you know, so. And you can engineer all that stuff. Raise your hand if you do. Raise your hand if you create electronic music. Anybody in here ever do that? Good. Am I talking correctly? Yeah. I've never made music electronically. I know you can do it, but so what I just said was kosher? Good. Have you made any good music? You laugh. I guess not. No. So you enjoy doing it. Have you made a lot? Good. You want to send me a link? Do you have anything on? No, maybe I better not ask. Anyways, if you have something on SoundCloud that might be good for everybody else to listen to. Yeah, okay. Send me a link. Through web courses. Yeah, good. Yeah. All right. So let's talk about one more thing, and that's the intensity. The decibel scale. I want to give you just a little blurb about this. Okay, so here's my diagram that I started the hour with, and let's just focus in on this part of it, the beats part. And the decibel scale is related to the amplitude. Right now, the amplitude of a sound wave, the square of the amplitude is actually how you calculate the intensity. Now, the intensity is the number of joules per second hitting a square meter of surface. Now, nobody has an eardrum that's a square meter. So, but you know, they calculate it out. You know, so many watts per square meter, and that's what sound intensity is. So, but just to review, in terms of this beats diagram, up here on the left, you have a big amplitude, all right? And so that's where it's going to be loudest, okay? If this were ocean waves, this is where you'd have the biggest rogue wave. If it's audio signal, this is where you'd have the loudest sound. Now, right over here, where the amplitude is pretty pokey, you're going to hear something, but it's going to be pretty faint. Okay? Pretty small amplitude. The square of that is going to be pretty small, right? But it's not zero. Not here anyways. So if this were ocean waves, this would be where the flat or relatively flat water is. All right? So right about there is it. And down here, here's the wavelength of the beats and stuff like that. Okay, now so we're not talking about wavelength here, we're talking about amplitude, which is the vertical displacement away from equilibrium. That's why I have the blue equilibrium line here for you. Now, the decibel scale is basically about the exponents in scientific notation. Okay, so the intensity here this is the actual physical measurement, watts per square meter. How many watts of power, how many joules per second cross the eardrum or hit the eardrum? Okay, if you have a lot of joules per second per square meter, then you have a lot of intensity. Okay, now the power of 10 at the threshold of human hearing is 10 to the minus 12. 1 times 10 to the minus 12 is the commonly accepted threshold of human hearing if you measure it in watts per square meter. Right? So how much energy is deposited per second? for a square meter of eardrum. All right? And since nobody has a square meter of eardrum, you just divide by whatever the area of the area of the eardrum has got to be like a few square millimeters. It's not very big. But anyways, that's considered 0 decibels. Now, 20 decibels is a whisper. Excuse me, barely audible is 20, and 40 decibels is a whisper. So if you're sitting next to somebody, you can whisper, and electronic music. What is your name again? Kim. Yeah, Kim, right? Mick. Or just the opposite? Yeah. Okay. Mick, you were just now, what's your name? Sitting next to Mick? Yeah. Mick was just whispering to Kristen. Now, I could hear him. I couldn't really make out what he was saying. I couldn't tell him, he's, let's go for lunch at Chick-fil-A. I couldn't figure out what he was saying, but I could see his lips moving. I could hear him blabbing. But it was a whisper, okay? 40 decibels approximately. All right? Now, if you look at the exponent, it's 4 powers of 10 up. So it's from negative 12 down here up to negative 8, right? So it's another 4 power. So decibel-wise, that's 40. So the baseline is 10 to the minus 12. Down here, really faint, just barely able to hear it. And then 10,000 times louder than that, 10 to the 4 powers of 10 above that, is 40 decibels, right? Traffic, city traffic, 70. Oh, I'm sorry, I read that wrong. Whisper is 20. Library, 40. 10 to the minus 8. City traffic, 70. 10 to the minus 5. Subway train, if you've ever been to New York, you know that they can be really loud, especially if you're right up next to the, up to the train, you're on the platform, just a foot away from the train, it can be really loud. Forget about a rocket blast off over at Kennedy Space Flight Center. You don't want to I think even a mile away, it's probably really loud when those babies take off. In fact, I think you can actually see the acoustic waves in certain conditions when these big rockets take off. They become visible because they heat up the air, so the air is so hot it glows. It's interesting. I'm going to have to look into that. Anyways, rocket blast off, 180 decibels. Wow. You're all the way up to 6 times 10 to the 0. All right, so every 10 decibels means another power of 10 in the watts per square meter column. Okay. So decibels is kind of a artificial rating. The thing you actually measure is watts per square meter. So you have a little microphone, and it's got a circular cross section. And you measure the diameter, and the radius, pi r squared, that gives you the area. And then it causes so much motion. And, you figure out, okay, that's, so many joules of energy per second. And that allows you to figure out the sound intensity, okay? So that's the decibel scale. And I'll just invite you to read about it. This is table 7.4. It's a nice little table. You can read about it in different places on the internet, stuff like that. By the way, this table encodes something that we're not supposed to talk about in this class: logarithms. Yeah, we're not supposed to do trig, calculus, or logarithms, but this is actually in this table, so just don't tell anybody. All right, I want to talk about electrons and atoms. We're heading towards the periodic table. Go ahead and jot down this web address, webelements.com. It's a really, 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 really nice one of my favorites websites. I mean, I don't screw around by reading it, but in terms of looking up stuff that I need for class, it's a good website. For screwing around, I go to Reddit, other places. The periodic table is important because every cell, like this one, encodes the basic structure of the element. So the element carbon, very plentiful on the surface of the Earth, has its structure encoded here. The 6 signifies that in the nucleus there are 6 protons, and in a neutral carbon atom there will be 6 electrons. Okay, a proton is positive charge, the electron is negative, so 6 and 6 means you've got a neutral atom. 12.011, that's the atomic mass. Right? And that means that in the nucleus, you've got 12 objects. Now, 6 of them are protons, and 6 of them are going to be neutrons. Neutrons are about the same mass as a proton. Right? And so this tells you the basic structure. In addition, as a table, when all the cells are lined up, they're not just lined up in any old order. They're not lined up in a circle. You know, they're not lined up in a parabola. They're lined up as a rectangle, certain number of rows, certain number of columns. Each column and each row has identifiable patterns in the bulk properties. So if you take a bulk of carbon and a bulk of whatever's below carbon on the periodic table, and then whatever's below that, you're going to find similar properties in that column. And then when you look at the rows, you'll see a progression of values in each row. So the second row of the periodic table where carbon is, you'll see from the left side over here with lithium all the way over to the other side with neon, you're going to see a progression in physical properties. And then the row below that, you'll see a similar progression in physical, you know, like, for instance, diameter. So the e pluribus unum concept can be, is implied, or the pattern in the e pluribus unum properties, bulk properties, is kind of implied in the fact that we've stacked up the periodic table the way that we have. We stacked it so that you could say this column, this row has certain properties and certain trends. Kane?
What is the 6 and the 12.011
The 6 is the atomic number. It tells you the number of protons in the nucleus, the number of electrons in the neutral atom. The 12.011 tells you the mass of the atom, the average mass of the carbon atom, and because it's in atomic mass units, it tells you how many things are in the nucleus, 12. Since you know 6 of them are protons, that means the other 6 have to be neutrons. So it encodes the structure. And then the whole periodic table itself encodes a lot of different physical properties, so it's kind of cool. And we'll be talking about periodic table next week. But before we do that, I want to talk about basic concepts of the electromagnetic interaction, because that is why the periodic table has the shape and the patterns that it does. Chemistry is all about electricity, the electromagnetic interaction of electrons in one atom with electrons and protons in another atom. Now, even in the days of the ancient Greeks, they knew that certain things were kind of cool. If you had a piece of amber, you know, a fossilized resin from a pine tree, from sap of a pine tree, if you took resin and you rubbed it on your toga, you know, you're sitting around in the forum in ancient Rome, and you rub rub that amber on your toga, it'll pick up little pieces of papyrus or little threads, you know, or even, you know, a human, you know, pluck out a hair, it'll pick that up. And it's, you know, today we call it static cling. You know, you take stuff, you put stuff in the dryer, you forget to put in a sheet of cling-free or bounce or something, all your socks stick together, stuff like that. Okay, it's because of static electric charge. Now, the guy that figured out the object that is present when we have static cling, you know, is J.J. Thompson. And he is the one that discovered that electrons are particles. You know, you've been learning about electrons for, you know, since 5th grade science class, I suppose. And that's because J.J. Thompson figured them out. By the way, the word electron, excuse me, every day, every Tuesday and Thursday, something strange. The word electron comes from the Greek word for amber. You know, in the ancient Greeks, you know, the Spartans and the Athenians are talking about amber. Yeah, I'd like to, you know, trade some amber with you because it was considered a precious stone. They would use the word electra. In Rome, electrum. So we use the word electron for it. Now, in the days of J.J. Thompson, they had found that certain radioactive substances emitted 3 different kinds of rays. You know, so like radium and all the different radioactive substances, they were starting to isolate them. And what they found was that there was 3 different kinds of rays. An alpha ray, they called it, a beta ray, and then a gamma ray, or an X-ray, which we now know as an X-ray. Okay, so alpha, beta, and gamma. Now, J.J. Thompson knew that you could generate beta rays electrically. Okay, so what he did was he set up a beta ray generator, and then he channeled it into a vacuum tube so that there weren't any air molecules. And he said, let me see what this beta ray is made of. What is it? Is it made of well, he didn't know about photons. But, you know, is it an atom? They knew about atoms. You know, and they knew about, you know, different corpuscles, they called them. They knew about cells. You know, they had microscopes, so they knew that cells were what they are. So he said, what are these beta rays? So he set up this device. Here's a picture of it down here. Okay, and so you generate these beta rays, and then you accelerate them down. So in this gooseneck here, this little neck, you accelerate them, and then high and low, you have a positive and a negative plate. Here's kind of a schematic diagram of it. So you send those beta rays in from the left, and you send them between the positive and the negative plates. So go ahead and make a sketch of 2 plates. Signify one is positive, one is negative. In other words, you connect them to different ends of a battery. Positive end of the battery and the negative end of the battery. All right. Now the positive plate is, if the beta rays are themselves positive, they'll deflect away from the positive plate on top and toward the one on the bottom. All right. Now that's a problem because that's also the direction of gravity. But if you get something that curves upward, a negative particle, that means it's defeating gravity and it's being attracted toward the positive plate and away from the negative plate. All right, so that's nice. So J.J. Thompson said, all right, let me set up this device. I don't really know what I'm going to find, but let me set up a positive and a negative. And then out here at the end of the glass tube, the target, you know, and I've painted it kind of a light blue. It was actually paint that would fluoresce. So fluorescent or phosphorescent paint. It would shine green. And we still make, I think they still make green screen monitors. You know, the long, very thick, not flat screen, but a big, thick TV with a curved surface. And the inside of that surface is painted with phosphorescent paint of different colors. That's where the first color TVs. You can still get green screen monitors for computers. You may remember it from when you were a shrimpy little kid. Well, that's before, you know, most of you have had flat screens most of your life, I suppose, maybe. But before that, there were these big, monstrous TV. I have one in my office, actually. I bought a TV in 1995. And it's one of these big cathode ray tubes, CRT. Anyway, so if the beta ray goes through here, if it's negative, it's going to deflect upward, and it's going to cause this upper part to shine green. If it's negative, it'll do that. If it's positive, it'll dip downward and make the lower part of the screen here shine green. So, what did J.J. Thompson find? He found that the screen glows up here, above the line, and therefore that beta rays are positive. And in fact, by doing some F equals ma and a little bit of calculus, a little bit of trig, he figured out that they're not just positive, but they have a really small mass, and that they're very small particles. He discovered the electron. He said, the only thing this can be is a particle. And he discovered the electron. That's the discovery of the electron. Question?
I thought you just said that if
Kayla.
Shayna.
Shayna.
Yes. I thought you just said that if it's positive, it'll go downward.
If it's positive, it'll go downward. Okay, it'll go away from the positive plate towards the negative one.
So
If it's so this is negative. Yeah, did I say that this was positive?
Yeah.
Okay, so this means that the electron is negative. All right, sorry about that. So beta rays are negative, and similar analysis shows that the alpha rays are positive. Anyways, he did the electron. He showed that it's a particle. Now, let's look at this is a side note in red. In the metric system, the unit of charge is called the Coulomb, after Charles Coulomb, who figured out the electromagnetic interaction the same way that Sir Isaac Newton figured out the gravitational interaction. A positive Coulomb is the same as 6.24 times 10 to the 18 protons. Minus 1 Coulomb is the same number of electrons, because electrons are negatory and protons are positive. All right? And so, as J.J. Thompson found out, the electron is very, very teeny. Now, a few years after J.J. Thompson discovered the electron, they actually figured out the exact size, and it's really small. But in the metric unit of charge, and that's the household size unit, Coulomb of charge going through your household wires per second, this many electrons going through your wire per second is 1 ampere of electrical current. An ampere is 1 Coulomb per second. Your car, your house, you have fuses and circuit breakers that are sized in amps. Other devices have milliamps and even microamps. You know, your computer might have milliamp fuses. The electron charge itself, so the Coulomb is the metric unit, normal size. The electron charge, also considered to be the fundamental charge, which is the smallest one seen in nature, that's the quantity of charge on the electron itself. So the way that you figure that out is simply by saying this, that 1 Coulomb divided by 6.24 times 10 to the 18 protons means that the fundamental charge E, That's the symbol. And E stands for a positive number, so that's actually the charge on the proton. And minus E is the charge on the electron. It works out to 1.60 times 10 to the minus 19 coulombs per proton. Negative 1.602 times 10 to the minus 19 coulombs per electron. All right, so the electron is really, really, really teeny. All of chemistry is this big conversation between atoms and molecules in terms of what electrons are doing. And there's zillions of them. Every ounce of matter that you can see in this world has got many, many zillions of electrons, a huge number. So let's sum up what we know about atoms and so forth. Basically, here's the nucleus of a helium atom. 4 objects in the nucleus, 2 protons, 2 neutrons. Most helium in the universe is of that type. And a neutral helium atom is going to have 2 electrons orbiting. And so therefore, the cell of the periodic table for helium is going to look like this. You know, some periodic tables, they're styled a little differently, and some have extra information, but this is the basic information in most periodic tables. So that's the information for helium. So what we now think of is of an atom is a positive nucleus, with some protons and some neutrons, and outside flying around, zipping around really fast, a bunch of electrons. Now let's talk about some more about the concepts of electricity. So much for our little side note. How do you get something charged up? Well, one of the ways you do it is by rubbing. That's what amber was famous for. You rub a piece of amber, and it'll pick up little teeny pieces of paper and thread and stuff like that. If you think about, you may have noticed this combing your hair, that it'll charge up the comb, and what happens is the comb dislodges electrons. They tend to stick to the comb, and the hair loses electrons. So the hair tends to become positively charged, and the comb negatively charged. Right? And so that's what's called triboelectricity. Tribo. Triboelectricity, from the root word tribulum, which means to rub or to thresh. So you can also charge something up. If it's already charged up, for instance, by friction, you can then touch it to a neutral object, and the neutral object will acquire some charge. Okay, so you can charge things by contact. There's other ways to charge stuff up. For instance, polarization. Right now, go ahead and underline the word polarization, because it's kind of a cool concept. And sometimes you can develop charges by polarization. Sometimes you can polarize something and then it'll return to being nonpolar. But basically what happens is, for instance, if you charge up the comb is negative. All right? And so if you take a neutral piece of paper, like this little strip down here below the comb, if it's neutral initially, that means it has the same number of protons as electrons, roughly. Right? But if you bring it close to that negative charged comb, the electrons in the paper will kind of hightail it to the other side. So in this diagram, the electrons, Nicole, are going to kind of move down to the bottom edge of the paper. And that means up at the top, you have protons. And so the top of the paper looks positive. The bottom of the paper, in this diagram, looks negative. You've polarized it. Okay, there's a positive top, negative on the bottom. Polarized. My wonderful students, let me add another blurb here, a little side note about charges. A proton is about 2,000 times heavier than an electron. The mass of the electron is about 1/2000th of the mass of a proton. And a proton and a neutron are about the same. So an electron is about 1/2000th of a neutron, an electron is about 1/2000th of the mass of a neutron as well. Right? So either proton or neutron, they're about the electron's about 1/2000th of them. Or about 2,000 electrons will balance a proton or a neutron. Think of it that way. All right? So electrons are small mass compared to the proton and electron. So I say that in order to make the following statement. In almost any physical object, the things that move are the electrons. The protons don't really move because they're heavier. More mass, 2,000 times more mass. So if you have some electromagnetic repulsion, pretty much the things that are going to get repelled are the electrons. All right? And the protons are going to be left behind. All right? Question?
Like the planets around the sun.
No, it's not like the planets around the sun. You're thinking about atoms. Yeah, they orbit, but that's about it. Right? And they have a central force. But atoms are way different from planets orbiting the sun. Now, polarization. I asked you to underline that word. Here's an example of a cool experiment that you can do at home. Or if you're an elementary ed teacher or secondary ed teacher, you can actually do this for a science fair project. Okay? And that is, you take a comb and you charge it up. So the comb is negative, right? And then you turn the water on in your sink, like in the kitchen. And I've done this beaucoup times, any number of times. You take your comb, or actually anything, you take a piece of, any kind of a piece of plastic, and you rub it on your shirt, so it's negative. And then you bring it next to and you make the stream of water out, so don't turn it on full blast. Turn it on just so just go to the point where it's dripping, and then just a little bit more so that it's the thinnest stream that's not drips. Okay, so just a little bit more than dripping. Right, and that's what we got here. And you bring the comb right next to it, and there's going to be a net pull force on the water. It won't go straight down. It'll kind of dip over here to the right in this diagram. And that's because there's some net pull force, right, in that toward the comb. And that, my wonderful students, is because the water molecules are polarized. Let me repeat that. The water molecules are polarized. All right, now let's take a look at how that works. Here's an idealized diagram of an H2O. Two hydrogens and an oxygen. They form a V. The top of the V are the two hydrogens. The intersection of the two sides is the oxygen. It is a little bit wider than a right angle, so make it an obtuse angle. So it's a really wide V shape. And I always like to draw an arrow right through the middle of the oxygen to represent the polarity, the polar shape of it. Now, why is it polar? Electromagnetically, it's polar because of the fact that hydrogen has a fairly simple structure. Most hydrogen in the universe is one proton and one electron. That's it. The bonding between the oxygen atom and the hydrogen over here, this dotted line, and this hydrogen atom and the oxygen, this second dotted line, that bonding is because the one hydrogen, the one electron that each hydrogen has is getting shared with the oxygen. Oxygen would like to get 2 more electrons. It does that by sharing, okay, electromagnetically. It's actually an interference effect called a covalent bond, okay? The polar molecule is therefore going to have an electron somewhere along this dotted line and somewhere along this dotted line. Now the other end of the out here, the proton is going to be far out along that dotted line and far out along this one. So the hydrogen end of the water molecule is going to be positive, right? Now, that electron somewhere on this dotted line and fairly close to the oxygen is going to repel the 8 electrons that oxygen comes with normally. It's going to repel those to the other side of the oxygen. So that means, can you turn the light down to 0? All right, I want you to look at the colors here for just a second. Now, I've made this far end of the oxygen blue to symbolize blue for electrons. That's the negative end. The electrons of the oxygen tend to push themselves or to rearrange themselves to that end. They're trying to get away from the electron that's over here, somewhere on this dashed line segment, and this one too, right? And then by the same token, this end of the hydrogen and this end of the hydrogen over here, that's reddish to signify that that's where the proton is. The proton's out there, and so this tends to be the positive end. The hydrogen end of the water molecule is the positive end. The V-shape end of the water molecule is the negative end. So go ahead and make a note of that. Regular lights, please. Okay? The hydrogen end is the positive end. The V end, the oxygen end of the water molecule, tends to be a little bit more negative. All right? Now, if you bring, now here I actually brought the comb in. Here's the comb, right here. And it's negatory. So it's going to repel the oxygen end, but it wants to pull the hydrogen end. And so here's what happens. Take a look. Watch now. Animation time. Here we go. Ding. All right. It polarizes. It rearranges every H2O in the drop of water. In every drop of water. And when that happens, net pull force toward the comb. Now, I have a clicker question for you. Go ahead and get your clicker out. Yeah. It is moving fast, but still you can, that's why I don't have sharp colors here. There's no sharp boundaries. They're kind of, the colors are kind of gradient colors. What that means visually, it tells you that the electron cloud on that side is going to be a little bit stronger than the electron cloud on the other side of the atom. Okay, so that means that that's going to tend to be slightly negative over there, and then the other end is going to be positive relative to that. But yeah, I mean, if we were to do the full quantum mechanical picture of this, you could do it, but we're going to use the colors to help us figure it out, help us think about it. All right, quicker questions. Question number uno. The water exerts what? A leftward pull force? Is that true or is it false? Go ahead and click. And you better not answer E. Like some, don't, no, I said no. Don't do, you guys are busting my chops now. It's fine. I can figure out who's voting for E. Easy. Good. There's still some of you. Don't try to mess with Dr. B. I can figure out who's burning my chops. Good. All right. Anyways, make your decision here. $15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, see, go ahead and show this. Good. Nobody voted for E, but a bunch of you voted A is correct. And let's go back to the display. A is correct. The other ones, no. Newton's law applies to all forces. C, true, but the pull forces, third law of forces don't cancel each other out. Because they act on different things. If the comb is pulling the water to the right, the water is pulling the comb to the left. But those you don't really say those forces balance because they're not acting on the same thing. They're interaction forces. Next question. Why is the net force? In this picture to the right. Read carefully. Make a decision, make a vote based on what you think is correct. You know, what you... Yeah. Oh, yeah, you have to hit the send button on this one. Vote for your A, B, C, D, or E, and then hit the send, sorry. And if you're not getting it, hit the refresh key and try to send, and then hit the send key with your answer. You got to remember that. You have to remember that when we switch over to this kind of question. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. Yeah, you have to refresh it. Don't worry. Get the next question. Come show it to Darian. Come show it to Darian. Correct answer A. And B. And C. So it looks like about, 91% of you voted correctly on at least A, B, or C. So you'll all get dineros for that one. Okay? And now I want you to jot down why that is correct. First of all, you know, your comb is over here on the right side of the screen. That's negative. It's not displayed, but it's over here. So just think of the right side of the screen as negatory. Okay, now your positive end is closer. Your negative end is a little bit farther away because it rotates into place in this idealized view. All right, now the negative is going to be repelled from the comb, but it's further away. And just like with gravitation, the further away it is, the weaker. So the blue is going to be repelled, the oxygen end is going to be repelled, but it's not going to be as strong as the attraction of the hydrogen end. All right? So, weak repulsion to the left, coupled with strong attraction to the right. Ching! All right. It's, oh boy. I still had some more questions to ask. It's 1:20. Go ahead and be dismissed. Homework will be ready by tomorrow morning, if not sooner. You're dismissed.